Hello everyone. In last two lectures, we have studied semiconductor physics, diode construction and operation, voltage and current characteristics of diode, and diode models. We have studied all three different diode models in our last lecture. In today's lecture, let us study half-wave rectifiers and full-wave rectifiers. A complete power supply. Student, for any electronic product, we require a power supply. Here I have shown the basic block diagram for power supply. This input we get from NECB. In India, we get 230 volt 50 Hz input from NECB. So this voltage is given as the input to the transformer. This transformer is used to step down the input voltage. Step down means if my input voltage is 230 volt 50 Hertz, then I can reduce its voltage. Okay, so here the output of transformer which is shown here, it is a step down voltage, but it is AC voltage only. Then this AC voltage is given as an input to the rectifier. Here in this box, you can use either half-wave rectifier or full-wave rectifier. If I use half-wave rectifier, then output of that half-wave rectifier will be something like this. In half-wave rectifier, it will conduct only during positive half cycles of the input supply, and hence I am getting output only during positive half cycles. I'm going to explain you in detail this particular block today. Then output of this is given to the filter. Just see the output of filter. Instead of this, you are getting filtered output. Then this filter output is given to the regulator, and output of the regulator is given to any particular load or to a particular product. So basically, this power supply is used to convert AC signal into our required DC regulated voltage. Okay. Now let us study first of all about this rectifier block, and then we will go for transformer. Half wave rectifier operation. Student, in this circuit, I have given AC signal, AC bias to this particular diode. Okay, and here again RL is the load resistance is connected, and we are going to measure output across this load resistance. Now, what is the input? See here, the input is AC input. This AC input is applied to this diode. During only positive half cycle, your diode will conduct. During negative half cycle, your diode will be reverse bias. And we know that in reverse bias condition, your diode will behave like an open switch. Okay, so it will not give any output. So only positive half cycle you will get at the output. So during positive half cycle of the input signal, see here, I am getting only this much output. Now student, we know that in forward bias condition, only after cut-in voltage, your diode will turn on. Okay, so not at exactly at 0, but somewhere here at 0.7 volt, your diode will start conducting, and you will get such an output voltage for a period this T0 to T1. During negative half cycle, what will happen? During negative half cycle, this diode will be reverse biased. Whenever you reverse bias a diode, it will behave like an open switch, and hence you won't get any output during reverse bias condition, any voltage across this. You will not get any voltage across this resistor for a period T1 to T2. So if you see the output of your half wave rectifier for 3 input signals, or for, I'm sorry, for 3 input cycles, then your output will be somewhat like this. See here, I'm considering 3 input cycles. Okay, so during first positive half cycle you will get output, then during first negative cycle you won't get any output. Again during second positive half cycle you will get output, again no output during negative half cycle, and during third positive half cycle you will again get output. The average value of half-wave output voltage will be given by a formula. See here, Vp upon pi. What is Vp? Vp is the peak value of this particular cycle or wave. This is a peak value. Okay, so you have to consider this peak value, divide it by pi, then you will get the average value. 1 upon pi is nothing but 0.318. So you can write 0.318 into this Vp as it is. This formula is used to calculate average value of the half wave output voltage. Let us solve a simple example based on this. What is the average value of the half wave rectified voltage in this figure? Students, observe this figure carefully. One waveform is given. The peak voltage is 50 volt here. Okay, so substitute that peak value here. Instead of Vp, you will substitute peak value 50 volt upon pi. Calculate that value, which is equals to 15.9 volt. This is the average voltage, output average voltage given by half wave rectifier. Effect of barrier potential on the half wave rectifier output. As I told you, for every diode to turn it on, you require some cut-in voltage. If I am using silicon diode, then this cut-in voltage will be 0.7 volt. So if I give input Vp, that is a peak value of an input signal Vp, then if I measure output across RL, then it will be Vp voltage minus 0.7 volt. If I am giving here 10 volt peak voltage, then what will happen? 10 volt minus 0.7 volt is nothing but 9.3 volt will be your output, because the cut-in voltage required for this diode will be 0.7 volt. That much will be the voltage drop across that diode. Let us solve one more example based on this. Draw the output voltages of each rectifier for the indicated input voltages as shown in figure. Two different diodes they have used. The first diode which is used here is a rectifier diode 1N4001, and another in this circuit, the another diode they have used 1N4003. Let us consider the first circuit. The input for this diode they have shown here plus minus 5 volt sinusoidal signal, AC signal is the input, and output of this diode is given to this load resistance, and the another terminal of the load resistance is connected to the ground. So when during positive half cycle, this particular diode will turn on and the current will flow in this direction from anode to cathode through this resistor to load. Okay, so let us calculate what will be the output voltage in this condition. The peak voltage for the circuit will be, we have seen formula, the peak voltage. What is the peak voltage here? 5 volt minus this voltage drop. Peak input voltage 5 volt minus this voltage drop 0.7 volt. So output voltage across that resistor will be 4.30 volt. Okay. Now consider second circuit. The same circuit, only here if you observe the input signal, then it is having amplitude 100 volt plus minus 100 volt. So what will happen? This 100 volt during this positive half cycle, your diode will conduct. Current will flow in this direction and you will get voltage drop across this resistor. During negative half cycle, what will happen? During negative half cycle, your diode will be reverse bias. It will behave like an open switch and no current will flow through this circuit. So the voltage drop across this will be zero. So during positive half cycle, see here, 100 volt minus 0.7 volt, which is equals to 99.3 volt will be your output voltage. And see here, both the outputs here I have shown here in the slide. So you will get output only during positive half cycle and 0 volt during negative half cycle. Now here, you have to consider peak inverse voltage. Student, whenever I am applying sinusoidal signal or AC signal as at an input to this particular diode, we know that during positive half cycle, your diode will conduct, current will flow, and you will get voltage drop across this diode. But during negative half cycle, your diode will remain off. Off means what? It is an open switch. Nothing, no current will flow through the circuit. So whatever reverse voltage you are applying, that voltage we are applying to this diode. So what is peak inverse voltage? The peak inverse voltage equals the peak value of an input voltage, and your diode should be capable of withstanding this amount of repetitive reverse voltage. I, the meaning of this, if I'm using input signal, say plus minus 50 volt, then during positive half cycle and during negative half cycle, I'm applying 50 volt to this diode. So your diode rating should be such that it should be compatible with that particular input signal. Typically, your diode rating should be 20% higher than the input we are applying at the input side. So that is a peak inverse voltage, the maximum inverse voltage which will be applied to a particular diode, and your diode should not get damaged with that particular voltage. Okay. Now student, if you refer the block diagram circuit, I'm just going back here. See here. So here I have told you that the MACB input 230 volt 50 hertz in India, that input is given to the as an input to the transformer, and the output of the transformer is given to rectifier, and rectifier could be half wave rectifier or full wave rectifier. We have studied half wave rectifier, and let us see how transformer couples input to that particular rectifier. So transformer coupling. Student, here I have shown one transformer. Okay, so this is the primary, N primary and N secondary. Number of turns at the primary, number of turns at the secondary. I am applying AC voltage here, and depending upon this turns ratio, I am going to get step down voltage at the secondary. Voltage at the secondary is denoted by V secondary. Then the secondary voltage is applied to the diode. Your diode will turn on during positive half cycle, it will remain off during negative half cycle, and you will get voltage across this RA. Now, transformer coupling, how it couples. So student, you must have studied this particular formula. N1 upon N2 is equal to V1 upon V2 is equal to I2 upon I1. What is N1, N2? N1, N2 means number of turns at primary and number of turns at secondary. V1 is what? The primary voltage, V2 secondary voltage. Similarly, I2 upon I1, secondary current upon primary current. Okay. So once you know this turns ratio, you can easily calculate. If the turns ratio is given to you and if the input voltage is known to you, then you can easily calculate output voltage and output current at the secondary. Okay, I'm talking about transformer, input side of the transformer and output side of the transformer. Okay. Now, let us solve one example based on this transformer. Determine the peak value of the output voltage. For a figure, if turns ratio is 0.5. Okay. So, N1 2 and N2 1. This turns ratio they have mentioned. They have also given you the input signal 170 volt peak voltage here. Okay. The rectifier diode is used, and this is our load resistance, which is 1 kilo ohms. And we want to find out the peak value of the output voltage. Now, here, what is the primary voltage? The primary voltage, which is shown in the waveform, which is 170 volt. The peak secondary voltage, see here, the turns ratio, as per the turns ratio, 2:1. So if you, now you know that N1 is 2, N2 is 1, and V1 is 170 volt, you can easily calculate V2. So V2 I can calculate, which is equals to 0.5 into 170 volt, which is nothing but 85 volt. This transformer is used to step down the input voltage. 171 volt input voltage is stepped down to 85 volt. Now I'm interested what is the output of a rectifier. The rectifier peak output voltage will be 85 volt is the input for this rectifier. And what will be the voltage drop across rectifier? 0.7 volt. So obviously 85 volt during positive half cycle minus 0.7 volt is nothing but 84.3 volt you will get across this resistor during positive half cycle. Is that clear? During negative half cycle, you will get output voltage 0. You will get output voltage 0. Now, let us see what is full wave rectifier. A full wave rectifier allows unidirectional current through the load during the entire cycle of the input signal. Output signal frequency is twice the input signal frequency. The meaning of this sentence is, if I give input here, suppose this is my input signal, then you will get output during positive half cycle also, as well as you will get output during negative half cycle also. And that's why it is known as full wave rectifier. So just see here, during positive half cycle you are getting output signal, during negative, during positive, during negative, and so on. Okay, so average voltage of this full wave rectifier will be double of the half wave rectifier. And the same formula here we have used Vp upon pi, only it is multiplied by 2. So whatever average voltage we were getting using half wave rectifier, the double of that we have received using full wave rectifier. One more example we will solve. Find the average value of the full wave rectifier voltage in the given figure. Student, here they have shown the waveform, and in which the 15 volt is the peak value. So you can substitute this peak value here. So 2 multiplied by peak value, that is 15 volt upon pi, very easy to calculate. You can easily get answer 9.55 volt. Okay, this particular center tap full wave rectifier operation we will study in next lecture. Till that, whatever I have taught you, please revise it at your level. Thank you. We will stop here. Bye bye.